Really cool. Yeah, thank you so much to the organizers for inviting me and for running this excellent conference so far. Yeah, so I'm going to be talking about, yes, a categorical framework for coherence theorems. I will warn you that when I talk about categories, I will be very explicitly referring to one categories in this talk throughout. I think there's a little bit of two categorical stuff going on in the background, but yes, like when I say category, I mean one category. So shift your minds that way for now. And yeah, and a little bit of applications to equivariant algebra, equivariant operands. This is all ongoing joint work with Jonathan Rubin. And actually, the one last thing on the slide is the date. I think I told some of you this, but today's actually my birthday, which I I didn't say that for applause, but thank you. I appreciate it. Yeah. I feel like that must be some version of the birthday paradox of like, yeah, like if you invite a bunch of mathematicians to a talk, someone must be giving a talk on the birthday. But yeah, I bring it up. I was trying to figure out how to tie it to this talk, so I'm not just saying it. And I thought way back, I think I was something like 10 years old, and for one birthday, I think some family friends knew I liked math and got me a book about the proof of the Poincare conjecture, which it was this pop math book, right? And I had no idea what was going on in it, but something that really stuck out to me, and I think really just like kind of like captured my imagination was a definition of the like they tried to sketch out the definition of a fundamental group, right? And the thing when we always see when we think about right like the definition of the fundamental group or right like loop concatenation in a loop space, right, is that the group axioms are right like they're a little tricky because associativity doesn't hold up to homotopy, which I think is sort of like where homotopy theory kind of kicks in, right? Like you have this situation where you want associativity to hold, but it only holds up to this like shifting of these, right? Like if you think of loop concatenation as going around a loop at double speed, it only holds up to this continuous shift here. And that just, I mean, for whatever reason, that stuck with me, and I guess it's fate that like I'm talking about this now. But yeah, I mean, right, like this is something we're all familiar with, but I want to just review this to set up what we're going to talk about today, right? Yeah, I mean, associativity holds, but only up to homotopy. And in fact, commutativity maybe doesn't hold because you can't always continuously move one loop to the other side, except a lot of times it does hold. And specifically, it does hold whenever we have a double loop space, right? Because then we have two dimensions and we can shift, right, we can shift one disk over onto the other side. I stole this little cartoon here from a talk that Eugenia Chung gave once. And right, and you can think of these as various additions in this double loop space parameterized by an interval that goes with these two endpoints. And each point on the interval tells you one way to compose, or I guess add to disks like this. But of course, we don't have to go in this direction. We could have also gone down the bottom. So really, we should think of addition in a double space as parameterized by a circle with a sigma 2 action to really swap, right? And the fact that this sigma 2 action actually connects to things that have a path between them is really this commutativity here up to homotopy. Except, of course, right, we might instead want commutativity up to higher homotopy, which means we want to fill in this disk. And there's two ways to fill in this disk. This is just my poorly drawn cartoon here. But you could fill in this disk either by when you have a triple loop space, you can bring the red sort of like I guess you have a ball at this point, the red ball up over the blue ball, or you can bring the red ball underneath the blue ball, sort of continuously filling the disk in two ways. Really, you get a sphere, and this still has this free antipodal sigma 2 action that expresses the homotopy commutativity. And then you can keep going. You can keep going all the way up to if you have an infinite loop space, which is equivalent to a connective omega spectrum, you can parameterize this addition by S infinity, which also has this antipodal sigma 2 action action, and you just keep filling this up and up.
Magic Eye, if I like look at it just right, will it like ooh it'll pop out?
Yes, one will pop out, one will pop in. See this, you'll be able to visualize S infinity, which is and the cool thing about S infinity, of course, is that it's contractible, right? Like you keep filling things in until it's contractible. And this is really the higher commutativity that we sort of like the highest commutativity that we can get here. And of course we can generalize this beyond binary addition, right? We can take n-area addition, and really we want all of these possible additions to be parameterized by contractible spaces, and each n-area addition, space of n-area additions has a free sigma n action on it. The freeness really makes sure that these are distinguished and we don't just get some sort of like the degenerate case here, but right, like that these are actually different, not commutative on the nose, but the fact that it is contractible means that we have commutativity up to homotopy. And of course, there's some more algebra going on here, right? The n-area addition really comes from plugging in a bunch of binary additions into each other, and it comes from plugging in binary additions into each other in many different ways. And you also have n equals 0, you have a unit, right? And so there's some algebraic relations here that, of course, you can then compile into an operad, right? And specifically here an E infinity operad, which is something where we have a contractible space of operations for each arity and a free sigma n action on each sort of operation space here. And so this was Peter May's insight back in 72, right, that these E infinity operads really express higher commutativity. And really an operad isn't interesting until you look at an algebra over it, right? And so these E infinity spaces are these structures that have this higher commutativity, right? So every infinite loop space is going to give you an E infinity space. We pretty much just saw that. And also, really crucially, the converse is true, right? Every connected group like E infinity space, you have to do a group completion, is going to be weakly equivalent to an infinite loop space, right? And therefore a connective spectrum. And so this gives us machinery to really characterize the space data, right, this connective spectrum, algebraically through this except there's still a lot of data that we have to work with here, right? Specifying an E infinity space takes a lot of data, right? You have to, for each of these sigma and free contractible spaces, for each of these O of n's, you have to specify for every point on that O of n a map from x to the n to x to express this addition. And you also have to make sure everything works with composition and your units. The fact that it's free makes it a little easier, but it's still a huge amount of data you have to specify. And so May went a step further to actually try to capture all this information in a spectric monoidal category. We'll get to that in a second, but first of all, I will also mention, right, like there are directions where we want to generalize this idea, right? We don't just care about spectra. We might want E infinity ring spectra, where the spectrum, right, like if the spectrum are groups of homotopy, right, we want our rings of homotopy, right? We want these E infinity ring spectra. And so we need to like capture this distributivity law somehow. Which isn't immediately obvious. In fact, right, like it's not clear that you can do this with a single operad, right? Like you need some sort of like something a little more creative than that. You also maybe want modules and algebras over these algebraic structures, right? With some sort of actions, right? And so you might need to go to multi-category land, right? Like colored operad. And you might also want to generalize this equivariantly. And so Hill, Hopkins, Ravenel saw that, right? Like when we work with equivariant spectra, right? We have these things called norms. Right, and in fact, these norms actually make, right, when you have a G action from some group G acting on your space or your algebraic object. And also these multiplications, right? They're going to interact in a certain way that gives you these norms. And you have n infinity ring, right? Like what are called n infinity operads, which are the sort of equivariant analogs of e infinity operads. And you actually have possibly many of these up to equivalence, unlike in the classical setting where you really only have one E infinity operad up to equivalence. And so, right, so if we want to get these n infinity ring spectra, right, n infinity operads that Mike Hill and Andrew Blumberg came up with, right, we also need to think about how to get these, right? And so, but just back to sort of the original story, right? Like just these infinite loop spaces, we can get them from categories, right? And right, so the solution to the fact that there's like this huge amount of data we have to specify for an operad algebra is to start with a symmetric monomial category, right? Take its classifying space, or its geometric realization, right? And that can actually give us go from categories to infinity spaces. And we can and we can attempt to generalize in this direction. And so to sort of lay out this process, right, like it's I think yeah, it's helpful to actually remind ourselves how we go about defining a monomial category in the first place. Unlike Sophia's talk yesterday, I'm not going to spare you from the commutative diagrams involved here. But I will we'll walk through these, right? And this is one of those definitions that I feel like people right, like don't like go over in detail. It's always like, oh, right, like it's a symmetric monomial category. You have these structures, right, you have these axioms. We're not going to cover these, but I think it's helpful to really like see what's going on here and see how the symmetric monomial categories, right, give rise to our E infinity spaces, right? And the idea is we are going to want operations of all arities, but we can generate these inductively, right? Like in order to obtain operations of all arities, it's really just generated from a unit object, a nullary operation, and a monomial product functor, right? A binary operation. And so that's really all we are going to need to define to start off with. But in order to have these higher, right, these homotopies between these, we're going to want to specify basically one simplices in right, that connect all of these n-area operations, except those are also going to just be generated by basically four different classes, right, of these things. Right, and so we are going to have isomorphisms between our operations that are then going to be realized into right, homotopies between our operations, right? And so we have left and right uniters, right, lambda and rho here going for in our sort of unary, right? That's the word. Unary operations between one tensor A and a tensor 1 to A. We have our associator, which I'm going to always draw in this direction, going from parentheses on the left and parentheses on the right. But these are all going to be natural isomorphisms for this metrical category at least. And two right, and so this is going to connect right like two operations in our ternary operation space. And we have a braiding, right, connecting two binary operations. But we still are going to want higher homotopies between these homotopies, right? And so we need to generate those all as well. And it turns out that you actually only really need 5 axioms to generate basically all of the higher homotopies, right, at all levels that you need. And these are going to be our equalities between the isomorphisms between these operations, right? So I put some symmetric and here because if you just want a monoidal category, you're not focusing on commutativity yet. These are just the 2 axioms you need, right? You have this pentagon, right, of associators, because there's 4, basically because there's 5 ways to parenthesize 4 objects, and you want all 5 of these to be connected by some simplex here. And then there's also these multiple ways to multiply 2 objects together if you stick an identity in the middle. Yeah, and you want all of these to be equal as well. And then if you also introduce a braiding, right, you have three more diagrams, right? You want the braiding to be its own inverse, you want braiding to behave well with our uniters, and you want the braiding to behave well with our associators. And right, these are basically what you would expect. It feels like a little bit like coming out of nowhere, but like this is kind of like right, like what you how you would expect these to interact together. And we're actually gonna see sort of like where sort of all of these really come from and why we're gonna right like why these actually generate all the equalities we need. And yeah, and but right, so how do we state what do I mean by generating all the equalities we need? How do we state this? Well, this was right, this was McLean's definition. I don't think actually in this original 63 paper he called these symmetric monodal categories, but this is where he laid it out, and where he proved his coherence. So to state this coherence theorem, I'm going to give some definitions. I don't know that these are the standard terminology, but they're the ones that sort of make intuitive sense for me for now. But so right, so we can think of our operations on a symmetric category as these functors from C to the n to C, and these are going to all be generated by right composites of products of permutations, permuting our variables, taking monoidal products, and the unit one, right? And so I'm gonna usually write these, right, like, and we usually see these written as where a tuple of objects get sent to, right? So if you have zero objects, they get sent. You can send them to just the constant one, right? So that's the one zeroary nullary operation. But of course, we have infinitely many unary operations because we can just stick any number of units everywhere. We have a bunch of binary operations. We can have x1 times x2 or swap them around. And again, stick units everywhere, stick parentheses everywhere. And of course, right, like the n equals 3 case, we keep going, right? And now you have right, like 6 different ways to arrange your variables and so on. But then somehow all of these operations in each arity are going to be isomorphic to each other and isomorphic in a unique way. And the or in a canonical way, and the isomorphisms between these are going to we're going to call these coherence maps, right? And these are going to be the maps that are actually generated by the associator alpha and the uniters lambda rho and the grading beta that we defined, right? And again, right, so these are going to be natural isomorphisms between our operations, given by, right, like generated by these via, right, taking monoidal products, taking composites. And so this is just a simple example, right? And then, oh, and one thing I should point out here is that all of these variables are different, right? Like just the way I define this means that you don't have one variable getting sent to two different slots showing up twice. And this is kind of crucial because we don't want to think about coherence maps that, yeah, there's some like kind of degenerate, not degenerate, but diabolical, right, cases that are, right, like if we have x1 tensor x1, right, we actually don't have a canonical map, one of these maps generated by these things between x1 and x1, right, because we have an identity, but then we also have a braiding, and we really don't want these to necessarily be equal. They're often not equal, right? So we're going to make all the variables different, and that takes care of that exception there. And so McLean, a statement of McLean's coherence theorem that he showed is that for any symmetric monodal category, there is a unique coherence map between any two n-area operations, right? There's a canonical one of these. And this is really the key that makes this whole thing work when we then take the geometric realization. This is what gives us our E infinity. Right, like this lets us see symmetric monodal categories as E infinity algebras and categories, and is what gives us these right E infinity spaces when we geometrically realize. And this we can take this a step further if we introduce two monoidal operations on a category that distribute over each other. And so a decade later, Laplace showed a coherence theorem for symmetric bimonoidal categories, right? So we have two monoidal structures, a plus and a times, and so we have to actually add a couple of extra natural isomorphisms, something that tells us zero it's multiplied to 0, and two distributive properties, one on the left and one on the right. And so then for any symmetric bimonoidal category, there is going to exist a unique coherence map between any two what are called regular n-area operations that have the same underlying polynomial, right? Like if we view right, like all of these as polynomials where we don't care about where things commute, right? And distribute, then any two operators have the same polynomial are going to give us two isomorphic operations. And regular, again, right, like it's this condition to avoid cases like this. We are going to want distinct summons, right, in our polynomials, and then also distinct factors in each summand. But crucially, this doesn't leave out cases like, right, x2 tensor x1 plus 1, right? Because right, this is still regular, even though a variable can appear multiple times in this, which is the thing that makes this pretty much impossible to model with just a single operad. You need to be a little more creative. You need to use Peter May introduced operad pairs to deal with this. You can also just think about, right, like you can also view this multi-categorically, right, like an operad it's an operad algebra in a category of other operad algebras. But you have to, right, and then you have to think about like how to deal with this distributivity condition. And right, but May's insight here was that given these two, right, like given these two coherence theorems, we can then use classifying spaces to get from symmetric monoidal categories to E infinity spaces to spectra. And then also from symmetric bimonoidal categories, right? He calls these permutative and bipermutative categories, which are the strictified versions of these. But you can only strictify these because you have this coherence, right? And right, these right, so symmetric bimonoidal categories go to E infinity, what are called E infinity ring spaces, and then become E infinity ring spectra. But again, I'll remind you, right, like some of the other things we want, right? We also want modules and algebras, right? And we also want to do all this equivariantly and maybe a lot of these at the same time, right? And so there have been a lot of historical developments here. This is just a quick little history here. I've been talking about May's, right, like infinite loop space machine, but of course you can, right, like the same story is holds for, right, like Siegel's K-theory functor, which May and Thomason then showed are actually the same, right, about the equivalence. And then, right, to generalize this multiplicatively, May introduced operad pairs to give a multiplicative infinite loop space machine. And I should also mention that this is enough, right? These symmetric monoidal categories, Thomason showed that these symmetric monoidal categories model all connective spectra. Right, like these are enough to give you all connective spectra, even though, again, we only need to define things up to sort of the second level here, right? Like equalities of isomorphisms of our operations. And so, right, like with this much smaller amount of data, right, much more tractable amount of data, we see symmetric monoidal categories all the time. We can generate our basically any E infinity space. Then, right, in 2006, Elmendorf and Mendel developed an enriched K-theory multifunctor. And the enriched multifunctor part just means that then you can actually you can actually bring modules and algebras, right? Because this is multi-categorical, you can bring modules and algebras over and generate these as well, push those through the machine. 2010, Mendel gave another right construction in an inverse K-theory functor that actually much more recently, 21, 22, both Elmendorf and Johnson and Yao independently showed to be multiplicative, and so giving you a again, right, like generalizing Thomason's result to show that, right, these not only model all connective spectra, but do sort of, right, like preserves the multiplicative structure. Okay, but then if you want to do all this equivariantly, right, with some group G, I think Shimakawa was the first to develop an equivariant analog of Siegel's K theory. But then Yu and May more recently also generalized the May's infinite loop space machine equivariantly. But I don't think either of these versions preserved multiplicativity. And so in 2019, Bert Yu, Peter May, Mona Merling, and Helico Sorno. I think actually, Parajita reference one of these papers, right? Because they needed to show this pseudo-algebra stratification theorem to do this, but they came up with these genuine symmetric monodal G categories that are then become inputs to their multiplicative equivariant K theory. And Donald Yao further generalized this to an enriched multifunctor so that it could carry over algebras, modules and algebras. But I want to point out crucially that both of them defines these right the inputs to their machines again as pseudo algebras over some operad. So you still do have to do that whole specification at every right at every arity level, and that's great, but it's still a huge amount of data you have to specify. So John Rubin, my collaborator, took a different approach and really just started with symmetric monodal categories, thought about, well, make everything have a G action. These are symmetric monodal G categories. And naively, if we just take the geometric realization here, these aren't going to have the HHR norms that we want out of equivariant spectra. And so John Rubin introduced basically a categorical norm on these symmetric monodal G categories, just another piece of data, and one more coherence axiom to deal with that piece of data. And then, of course, had to go through the entire MacLane proof and then generalize that proof to show that these were also coherent, thus showing that these, when geometrically realized, give you the n infinity spaces that you want here. And so again, right, like taking again, right, just finding sort of this minimal amount of data that you need to generate all of these higher homotopies. So that's what we are gonna try to generalize here, right? Thinking about okay, right, like if we want all of these things, right, we have equivariant right we have equivariant infinite loop space machines with generated by this small amount of data, but what if we want equivariant distributivity? What if we want equivariant modules and algebras with actions, and so on there. And so in order to get these machines, we're going to need to prove more coherence theorems and also think about, right, like what structures we're going to want to add to symmetric monodal categories or similar in order to generate these. So right. Yeah, so I should preface this by saying, yeah, one time Mike Hill said something to me, which was that this is why nobody takes category theorists seriously. It's because you all come up with these cute names for everything. And so I have to apologize for this name. An actagory is a category acted on by a symmetric monodal category. And so Matteo Capucci and Bruno Gavranovic, actually here in Scotland, showed a coherence theorem for actagories in their paper, Actagories for the Working Amthematician. Um, and right, and they also they showed this with kind of monad and pseudo algebras over monad methods. Again, right, like and I think they actually basically say coherence, right, like that MacLane's proof can be generalized to this setting, but which is true, but I think you have to if you want to unpack this proof to see how this coherence comes to life, you really need to right like go through MacLane's coherence in this kind of case where you have this extra action. And which is what John Rubin did when he added his norms to his equivariant symmetric monoidal categories. And so really the question now is, right, is there an equivariant norm symmetric bimonoidal category? Can we take Laplace's proof and tack on these norms, both additive norms and multiplicative norms, to these categorical structures? Are there lax versions of these, right, where we start, and what I mean by this is we maybe don't necessarily need these to be isomorphisms, right? Need these natural transformations to be isomorphisms. Not that we have a whole lot of examples of right categories with these structures, but what is actually required to generate these, right? When we take the realization, right, like it's gonna become just a homotopy anyway. So what can we start with to get these coherences? And can we also just like generalize this so we don't have to kind of like prove every coherence theorem one at a time, right? Like and rewrite the wheel here. And so this was what John and I were thinking about. I should also mention there's a paper by Mimram recently that is also trying to find a general categorical framework for this, but doesn't incorporate this sort of laxity that we're trying to think of, and like it's a slightly different strategy here. But yeah, and I should, right, why do I bring up this laxity, right? Well, Laplace, when he initially stated his coherence theorem for symmetric bimonoidal categories, he actually stated it like this. So he let his distributivities, I wanted to call these distributors, but there's something else called distributors, so I'll call these distributivities, right, these deltas here. He actually just let these distributivities be monomorphisms. And he said that there's at most one coherence map between regular and array terms. And here we have to phrase it as at most one coherence map because we can't, if we just have them going in one direction, we can't necessarily go backwards. But there's actually an implicit condition in Laplace's proof that maybe wasn't sort of pointed out, right? Like the statement of this theorem has been stated basically without this italics part for many decades until Donald Yao pointed out recently that actually there is this hidden condition in Laplace's theorem that actually not only do the distributivities have to be monomorphisms, every coherence map generated by these distributivities also need to be monomorphisms, which is okay if you have a closed monoidal structure, right? Because that's going to preserve your monomorphisms, but right, is not necessarily implicit like in this definition. And so you have these hidden conditions that you have to be very careful to check. And I wanted to point out that, right, like Laplace's original proof took 37 pages to like get this out. And then Donald Yao then took this and was like, okay, some of these are only outlines, and right, like we also have to clarify this, and then took another pages to like lay out, right, like exactly how you go about doing this. And I'm by no means claiming that with our methods, we are going to have any shorter of a paper here, but hopefully, right, like it means we don't have to like re-go through this every time that we want to prove a new coherence theorem. And so, right, we came up with this categorical framework for really thinking about these coherence theorems. Right, because there's really two parts of this problem. The first part is thinking about what are called, right, universal parameter categories. Basically, constructing a category from the ground up that is going to parameterize each of these monoidal structures. And then solving these coherent normalization problems that are posed by these categories. Right, normalization problems are right, like a way of thinking, well, right, like how do we right, like normalize something like this? Well, really by the end, we want to end up with something like after distributing. Okay, is the idea here, right? We want to put, right, we want to distribute everything out. We want to put everything in sort of this numerical order, and then put all the summons in a canonical order. So that we actually know that we can always end up somewhere, and that all of the ways of ending up that somewhere are going to be unique. And so that's sort of the outline I'm going to go through in these last however many minutes, 15 minutes. So Yeah, so first of all, I'll phrase these coherence theorems as these normalization problems. And this gets very combinatorial and like gets into rewriting theory, which is something right like logicians, computer scientists think about. But we're just gonna tack on a one categorical twist onto everything, because we actually care about these commutativity diagrams as well. We're calling these coherent normalization problems, and the way we want to phrase these is through directed graph, right? Set of edges, set of vertices, domain and codomain maps, and a set of marked edges, because we want to keep track of which edges in this graph we want to invert, right? We want to make invertible, like so that we can capture the Plaza's setting where most of these maps are invertible, but then some of them are monomorphisms. Then we also want to introduce
So inverting, you mean putting an arrow back in the other direction?
exactly. I'm just gonna stick an arrow back in the other direction to get this G I inverse. Thanks for thanks.
These include self loops, or do graphs not have self?
Yes, they could include self loops. Yeah. Yeah.
Have a self loop in your E, what happens?
You have a self loop. You give it an inverse. You just say, okay, this is the inverse, right? You label everything.
I
Right?
see.
Yeah. Yeah. I'm trying to think if there are. This is where we actually do want self loops, like in practice, but right, like in theory, this could like
Yeah,
have
sorry,
self loops.
continue.
No, you're good. Yeah, that's helpful to clarify. Um, and then we want a congruence on the free category generated by this directed graph, right? Where the morphisms are paths in this graph, that make these formal inverses actual inverses. But then the congruence also is going to do more things, right, to actually express our coherence axioms. And so we say that this CNP, right, this coherence normalization problem is going to present this quotient category that we get by quotienting out by this congruence. And then we say that we have a solution to one of these CNPs if we have a subset of vertices that are going to be what are called our normal forms for everything in this, right? Everything in this graph, right? And so we have a solution if there is going to be a unique element of this solution set that is going to be the normal form for each vertex in our graph, right? So that gives us our coherence map. It gives us at least one coherence map. I'm using a double arrow for this. I think I'm actually gonna, yeah, I'm gonna be using single arrows for like arrows in the graph and then double arrows for arrows in the free category. So this might be an identity, it might be a path. In the graph. But right, so this is going to be our coherence map, but then we also want our coherence maps to be unique up to tilde, right? Every pair of parallel morphisms here to this normal form are going to be tilde related, which of course then means when we actually take this quotient, right, it's going to end up as a coproduct of categories with these terminal objects, which are going to be all of our normal forms, which is exactly what we're going to want to parameterize our, for example, our symmetric monodal categories, and so on to have these unique coherence maps. And so
This is what kind of forces this to be terminal, is that?
let's see. Yes, unique forces it to be terminal, right? Or I guess, right, this condition forces it to be, or I guess both conditions force them to be terminal. Right, yeah.
So should I think about like this FGI inverse and then mod the relation as like the free category, one category,
Yeah.
which has like generated by finite or like finitely many symbols.
It doesn't have to be finite. There's no finite
like a
here, but yeah.
by infinitely many actually, right?
Yes, yeah. I guess the paths do have to be finite, but yeah. Yeah. Okay, here's an example, right, a little more concretely. A lax monoidal category is going to be a monoidal category. There's this ridiculously long NLab page that tells you all of the different laxities for like monoidal categories. But what I mean by this is just that the associator is going to go from left parentheses to right parentheses in that one direction, and the uniters are going to go from one unit to no units in that direction. And you can reason out, but of course you can actually combinatorially show that you can always get to something with all the parentheses leaning the right. And so these are some examples of like four area operations that we get, right? And we have various coherence maps, but of course, right, because of the pentagon axiom, right, we want these two coherence maps to actually be sort of related to each other. Yeah. And so this gives us a coherence theorem for Lax-Monodal categories that every four area operation has a unique coherence map to that particular operation there. Here's another example, right? Permutative categories, right? Where we take a symmetric monodal category, we make everything strict except for the braiding. And so these arrows are showing, I put double arrows on them because braidings want to be invertible, and I had a lot of fun coming up with this. I think the blue arrows are showing sort of braidings that are taking the whole thing, like taking two things here and one thing here and swapping them, for example, to get that, versus these red arrows are keeping one thing the same and then doing a swap over here, and we can get all 6 of these. And so, right, terms where all the variables are in order gives us a solution. But actually, we could have picked any representative here, and it would be the terminal object for these. This ends up being, right, when we present it, this ends up being a contractible groupoid. And so that, right, like that also gives us the solution. And so that gives us a coherence theorem for commutative categories, which is what we use to do our infinite loop space machine on commutative categories. Okay, but how do we actually define these CNPs? Right, these CMPs are going to present, right, what we call these universal parameter categories. And these are going to be the categories that parameterize our symmetric monodal categories, or whatever our algebraic structures and coherence axioms are going to be. And so again, we want to construct a graph, and then we want to construct a congruence on this graph. The vertices of our graph are going to be terms, right? We're borrowing a lot from logic here to make sure these terms are well formed. And these are going to be constructed inductively from variables, right, like x1, x2, countably many variables, from constant symbols, and from n-ary function symbols. Of course, you could think of the constant symbols as null-ary function symbols, but it's a little easier for inductive purposes to keep this separate. But yeah, and so you generate all of these terms inductively. But then you might also want to restrict these terms appropriately, right? Like these, right, for symmetric monodal categories, we don't want repeats, right? For symmetric bimonodal categories, we want regularity. And we also maybe only want to focus on x1 through xn, for example, to focus on once we interpret these as our operation functors as functors from C to the n to C. And then we can also type them as needed, right? So for categories, for example, we actually have 2 types of variables, right? We have these x's in the symmetric monodal category that's acting on another category with these y's, right? Like this. And so then we can, if we have, countably many types, right, we can then, right, like express all sorts of different algebraic structures between different categories. So these are going to be our terms. We're going to interpret these as our operation functors that we described. Then we need to describe the edges between these terms that are going to be interpreted as our coherence maps. So we're going to start by what we call atomic transformations. I think we're borrowing this from I can't remember if it's MacLean or LaPlaza that calls them these as well. Right, so these atomic transformations are going to be the ones coming from our, right, what I call our transformation schema. Using the word schema like in logic, where we, right, like it's just a list of rules that we're going to then substitute variables or substitute other terms in to generate all the possible rules we have, right? And this is really what we're doing when we're defining a symmetric monodal category, for example, where I'm giving you these 3, right, these 3 transformations, but really we can replace A, B, and C with any terms that we want here, allowing for substitution of terms. But so this is our schema. That's going to give us our entire family of atomic transformations that we're going to interpret as coherence maps via substitution of terms. And then we're going to mark some of these as invertible as needed. And then, right, we need more edges actually, right? Because we need to actually be able to tensor these together or operation these, I guess, apply the function symbols on these together, right? And also, and Yeah, actually just that for now, right? Because this is just gonna be the graph, and then once we have the graph, we're gonna be able to compose them together, right, when we take the free category. But yeah, so we're gonna take these atomic transformations, and then construct what are called basic transformations, right? Those are gonna be all our edges, inductively using our function symbols, and maybe sticking in some constants, let's see. Actually, yeah, sorry, maybe sticking in some identity transformations in every other slot on all of our terms. And so these basic transformations are just going to have one, just to make sort of the inductive process easier, just one atomic transformation each, right? There's just one alpha here. But of course, once we compose them together, right, any coherence map we want to make with these, we can always sort of factor into something like this with into a composite of these basic transformations. And we mark these at the atom is marked, right, for invertibility. Yeah, I know this is all very like just like kind of the logic feel of like really building this from the ground up, right? But just to give you this picture, and because I'm actually running, uh, I guess slightly ahead of where I thought I'd be at this point. Yeah, and then of course we have to define our congruence, right? We're gonna start with our coherence axioms. Again, we can think of this as a schema that we can then substitute terms into, but we're also gonna need to add certain relations for, again, the inverse law for marked edges. We want to make sure our function symbols are functorial. Doesn't matter which part of the function symbol we apply a transformation to first. And we make those related. And then we want to make our atomic transformations actually natural, right? So we're going to construct some naturality squares as well, and make those related. And then we keep inductively applying these function symbols with identity transformations, right? Again, just preserving that functoriality to generate our congruence, right? We need on our free category. And so our theorem then is that a categorical interpretation, this is a lot, right? But a categorical interpretation of the variables, constants, and function symbols, which are going to generate all our operations, the transformation schema, which is going to generate all our transformations, and the coherence axiom schema, which is going to generate our entire congruence, is going to then lift uniquely to a functor out of the category presented by the CNP that we've just defined to the interpretations category of operations and coherence maps, like the one for symmetric monomial categories we saw. So again, just from this like small amount of data, we're actually going to be able to like sort of uniquely generate this whole CNP here. And so therefore solving this CNP is going to then prove our coherence theorem. And right, so again, another example of this, right? If we solved a CMP parameterizing permutative categories, right, that's going to imply the existence of a unique coherence map between any two n-ary operations, right? So both of these have two 1x, 2x, 3, which is their normal form in the solution. But because these are invertible, that actually gives us a coherence map that way. So it exists. And then any other coherence map, I guess because these should be tilde related, is going to actually then make this tilde related to that one for uniqueness. And that proves the coherence theorem. In the last couple minutes here, I'll just mention, right, really last 0 minutes, I'll mention that we can solve our CMPs through a variety of strategies, right? The most basic, right, like these are just, like in addition to all the setup we've done, we've developed this toolbox to actually solve our coherence normalization problems based on the kind of questions that come up in right, MacLane's proof and Laplace's proof and John's proof for norms, symmetric monomial categories. Right, whenever we have two CMPs, we can take their coproduct, and right, like then the coproduct of the solution, of course, right, gives us the solution to this new coproduct. But then we can also do some like, we can push forward against various functors between these CMPs. We have to have some specific conditions, but basically it tells us we can expand the congruence relation without affecting the solution, right? If you think about it, that makes sense. You can also expand the marked edges set, right? Adding more inverses isn't going to change what the solution set is. there are situations, actually the permutative category situation, you can actually, if you think about what the CMP ends up looking like, it's right, you can it's very similar to the Cayley graph for permutation groups, right? Like showing the generators of the permutation groups. And so you can always solve a CMP on that translation groupoid for a free action from some group from the Cayley graph for their group presentations. You can also introduce what are called monovariants. I thought this was a more common term, but really this is just like an invariant, except it always goes down in one, right? And that is going to be, I think Yao calls it an inductive device to help you reason along these problems. And then also we have what's called a diamond lemma. This is adapted from Newman and 42. Hewitt phrased this as this sort of well-founded induction along these monovariants in 1980, but again, without sort of the extra coherence part, right? Without the tilde congruence part that we introduced. It doesn't really add too much to this proof, but right, to actually tell you what conditions we use to solve a CMP. And then also take another thing we can do is take quotients of CMPs, right? If we have part of it already solved, right, to get from the solution to a symmetric monoidal category from a monoidal category, we can quotient out all of the monoidal category parts and just focus on the symmetric monoidal category parts. And so all of these, right, like we have like a lemma for all of these, and then we can then put these together to solve our CMPs. Just for the sake of time, I'm gonna sort of skip over actually like delving into these. But feel free to ask me about them. I'll go right to the very end here. And yeah, and so right, like what we're hoping for, right, is to actually then write out, right, with these with all this machinery, right, another proof of Laplace's theorem, right? And then hopefully then we can build that tack on norms to get a proof of coherence for equivariant normed symmetric bimonoidal categories. And then our goal ultimately, right, going back to homotopy theory, is to try to make these our inputs to the Gumet, Merlin-Sonneau, or the Yao K theory. But then also have categorical structures and potentially also higher structures, right? Like I feel like this after Sophia mentioned symmetric monoidal bicategories yesterday, I'm just thinking like, oh, right, like that's also a messy coherence like theorem, right? Like how can we phrase that? But yeah, that's I'll stop there and thank you so much.
Any questions?